Okay, in this video today we're going to be looking at why is it that some substances that you would not think would be acidic or basic actually produce acidic or basic solutions. Two examples of this were what we tested in the introductory acid-base activity, and those substances were aluminum chloride and sodium bicarbonate. Both of those are ionic compounds, and what we tested were those ionic compounds dissolved in water. So these equations that we're looking at right now are the equations for the formation of those solutions. So we know that ionic compounds normally are solids at room temperature. We know that when we dissolve them in water, they dissociate into their ions. So aluminum chloride breaks up into the aluminum plus 3 ions and 3 chloride ions. And the sodium bicarbonate does the same, except it's got 1 sodium ion and 1 bicarbonate ion for every formula unit that dissolves. So when we think about looking at identifying Arrhenius acids and bases, neither of these have an H plus to be given off, and neither of them have a hydroxide to be given off in their formulas. Yet we find that aluminum chloride tested with a pH in the acidic range, and baking soda or sodium bicarbonate tested with a pH in the basic range. So we want to look at what's actually happening that is causing that change in pH from being neutral like you might expect. So what we need to remember, and what we'll be asked to do in our hydrolysis of salts lab simulation, is to look for the origin, acid, and base. And so what that means is, like, if I were to think about this is like a salt that was born from a neutralization reaction. So between an acid and a base, an Arrhenius acid and base, if there was a neutralization reaction, we know the products are water, which forms from the H plus and the hydroxide ions getting together, and then there's salt. And the salt is basically the leftover components from the cation from the base and the anion from the acid. So when I look at aluminum chloride, what I think about is the origin, acid, and base. So again, I'm looking at the anion, and if I put that with H+, that would give me HCl. So that's what I mean by coming up with the origin acid from the anion. Notice that I'm not putting the 3 down here next to the Cl, even though we saw that in aluminum chloride, and that's because, you know, H+ has a +1 charge. Cl- has a -1 charge, so there's just one of each in the formula. So when I think about that origin acid, HCl, that is hydrochloric acid. That is on the strong acid list. So when I think about strong acids, I should think about this, well, the definition of a strong acid is that it completely ionizes. So for every single formula unit of HCl, there'd be 1 H+ and 1 Cl-, and these two do not stick back together again. The reason I want to think about that is that when I look at Cl-, the reason that the H+ does not reattach itself to the Cl- is that the thing that's not written here is actually the water molecule. And we talked about the fact that H+ actually in solution attaches itself to the lone pair in a water molecule. And it's actually because that H+ is more attracted to the lone pair in the water molecule than to the Cl-, that's why they never reattach to each other again, because the H+ would much rather be attached to the water molecule. So when we think about then getting this chloride ion in solution via another means, so it didn't come in as a part of an acid, but rather this ionic compound, aluminum chloride. If I think about that, again, the chloride ion similarly is not able to pick up and attract H+ ions that are available as a part of the self-ionization of water process. So chloride ion just stays where it is, doesn't reattach to anything. And so, again, when I think about the origin acid being HCl, and what I understand about that as being a strong acid, that is a reminder to me that the anion that comes from a strong acid cannot and will not reattach itself to H+. Okay, so that's not doing anything. It's just purely a spectator, and that's not causing any acidity or basicness. But what is, in this case, is the aluminum. And so again, if I think about, okay, well, the aluminum ion, what would be the origin base for that if I combined it with hydroxide? The origin base for aluminum hydroxide would be, the origin base for aluminum would be aluminum hydroxide. So I have that written right down here. Notice I've got 3 hydroxides, since hydroxide's a -1 charge, aluminum's +3, so there you go. So The origin base aluminum hydroxide, well, this is not on the strong base list. So when I write the dissociation of this thing, what I need to remember is that there's actually going to be a fair majority of the aluminum and hydroxide ions that remain stuck together. So aluminum is going to be really attached to hydroxide ions more so than separating from them. So when I think about that then, well, what happens when I get this salt dissolved in water is that aluminum ion attaches itself to hydroxides that it gets from water. And if you think about if aluminum interacts with water and picks up hydroxides from it, well, what do you get left over if you take away hydroxides from water? You end up with hydrogen ions. So just looking at this top equation here. And so if there's an increase in hydrogen ions because we're basically stripping apart water molecules, we end up with a lower pH, and that pH then would be in the acidic range like we tested. So it's because of the origin base, it's because of the aluminum being able to attract and attach itself to hydroxides that leaves us with an excess of H+. The Cl- doesn't do that at all. And we end up then overall with an acidic solution as a result. So then we look at the baking soda, opposite thing is happening, but same kind of idea. So again, the sodium hydroxide would be the origin base that we would associate it with. Again, that's a one-way strong base. Sodium ions separate, they stay separate from the hydroxide ions when that dissolves in water. And so we do not see the sodium reattaching itself to hydroxide ions. When we look at the origin acid, so adding an H+ back to the HCO3, our origin acid would be carbonic acid, and that would, again, be a weak acid, so it's not on the strong list. And so we would find some H+ and some bicarbonate ions, but the majority of the bicarbonate ions would remain attached to that hydrogen in carbonic acid. So then when we think about these two pieces, we've got from our salt, we've got the bicarbonate ion, we've got the sodium ion. Sodium ion is not able to reattach itself to anything. The bicarbonate ion is, and what we actually find then is the bicarbonate ion combining with water. And again, water is amphoteric, so we see that in this first reaction, aluminum took away hydroxides and left H+. In this case, we have the water molecule giving up H+ to the bicarbonate and leaving us with the carbonic acid and then excess hydroxides. And so with the excess hydroxides in solution, that is going to give us then a pH of greater than 7, and that is why we end up seeing the the bicarbonate, sodium bicarbonate measuring in the basic range, because there's an excess of hydroxide ions that are released as a result of this interaction with the bicarbonate ion in water. So that is, in a nutshell, hydrolysis of salts. So again, if I have a strong acid and strong base component that are present in water, they're not going to do anything to the water, they're not going to interact, and we don't see anything but a neutral pH. If I have an anion from a weak acid or a cation from a weak base, those will interact with water and then give us a surplus of either H+ or hydroxide, and that is hydrolysis of salt.